Okay, so let's do, wait, what am I doing? Wrong page. Okay. Okay, sorry about that. Use the strong maximum principle to prove the following. Let omega be an open connected set. If G is continuous on the boundary of omega and F is continuous on omega, then there's at most one solution to this problem. That is twice continuously differentiable on omega and continuous on the closure of omega. There's a little bar there that's hard to see in the notes there. Okay, so we're going to do a very, very standard thing here is assume that U1, okay, let me get off on this tab here, sorry, U1 and U2 solve the equation, then set W equals U1 minus U2. We're going to show that W is equal to 0, which means U1 minus U2 equals 0, which means U1 is equal to U2. Then set W is equal to U1 minus U2. We have minus delta W equals minus delta U1 minus U2, which is equal to minus delta, minus delta U1 plus delta U2 minus delta U1 is equal to F. Delta U2 is equal to minus F because, minus delta U2, minus delta U2 is equal to F. So we get this, and that's equal to 0. Okay, so this says delta minus delta W is equal to 0. And W uses vertical bar. It means W restricted to the boundary is equal to U1. Sorry, I'm going to use vert. Sorry. Yeah, not vet. Vert minus U2 okay, well, U1 restricted to the boundary. Sorry. My goodness. I'm going quickly here. Too quickly. All right. Okay. Well, U1 and U2 are restricted to the boundary of both G, so this is G minus G, which is equal to 0. So, W satisfies W satisfies the following. W satisfies this is equal to 0, and W is equal to 0 on the boundary of omega. Okay. So I said use a strong maximum principle. You don't actually need the strong maximum principle, but the strong maximum principle can prove the weak maximum principle. I'm not sure why I put the strong maximum principle here. Okay, so we know that max omega. If I look at the maximum of W over the closure of omega by the weak maximum principle, this is equal to the maximum of W over the boundary. Let's say by the weak maximum principle, the maximum of W over the closure of omega is equal to the maximum of W on the boundary of omega, but that's just equal to 0 since W equals 0 on the boundary of omega. Okay, so the maximum W can get on the whole thing is 0. Thus, W, or U1 minus U2, which is equal to W, is less than or equal to 0. So this says that u1 minus u2 is less than or equal to 0. Similar arguments. Let me write here. So u1 is less than or equal to u2 on omega. Okay, so similar arguments, like if you do w, if you now run this entire argument again, but say w is equal to u2 minus u1, this is going to imply that u2 is less than or equal to u1 as well, and so u1 equals u2. See, a great way to prove two things are equal, if I want to prove A is equal to B, I can prove A is less than or equal to B, and B is less than or equal to A, and that proves the overall thing. Okay. Whoops. All right, that is it.